Good afternoon, everyone. Can you hear me fine? Okay. My name is Praveen Pillai. I'm a senior research scientist at HRL Laboratories. I'm currently leading a multidisciplinary team comprising 6 universities in the DARPA Lifelong Learning Machines program. Today, I'll be sharing with you some of what we have been doing in the program, some of our recent successes, and how they may be related to autonomous driving. As Tim Talty mentioned, the AI that I'll be talking about is something that happens in the field. So it's all a new kind of AI. And this new kind of AI requires new kind of hardware. So as I go through my talk, I want to challenge you to think beyond doing fast matrix multiplications. We really need to go beyond that. We're all excited about the prospects of AI. In the last decade or so, AI has achieved suprahuman levels of performance in image recognition, in Atari gameplay, and even the sophisticated game of Go. But despite all this, AI still lacks some very basic capabilities. Researchers have shown that even with very minute changes to the inputs, the current AI can fail catastrophically. So essentially, AI is very good in a limited, well-defined setting, like an Atari game, but then it is not very robust to open novel situations. Let's take the case of autonomous driving, where wrong AI behavior can prove destructive to life and property. Imagine an autonomous car that has been trained to perfection to drive appropriately in the correct lane and to avoid hitting obstacles. However, in fielded operation, if the car encounters a work zone for the very first time, it's going to freeze because its program was to be in the correct lane. And if the human worker actually directs the car to drive in the opposing traffic lane, which it was trained never to do, it's going to be very difficult. So what we want is the car to adapt rapidly to these novel situations. Another case is the situation where one or more sensors on the car can fail unpredictably due to changing weather conditions or damage or whatever. So even in this case, what we want is an ability to not freeze, not to throw an error message, but to adapt in a way that is not failure. So essentially, the data distribution that one encounters during fielded operation is very different from that used during training, and that is the problem. So for the new AI, what we want is, excuse me. Sorry. For the new AI, what we want is the ability to continually learn in response to the changing data distributions, generalize robustly to surprises, and to adapt rapidly to failures. So let's consider the current concept of operations. In the training phase, an autonomous car is trained to detect lane markings, objects, and drivable surfaces. Then a fleet gets deployed in the real world, where surprises abound. So sometimes, or actually many a times, the car hands off control to a human operator, or the human actually intervenes in the face of incompetent behavior from the car, or maybe there is a crash. So in all these cases, the log of the recent experiences leading up to each surprise event is sent to a cloud. And then the base model of the car is retrained or updated with all the billions of training miles combined with the new surprise data. If you just trained on the new surprise data, then the neural network that drives the car is going to be optimized for the latest surprise, but it is going to forget all the old driving skills, like being in the lane. So then after some tests and verifications, a software update is sent to the car several weeks or months later. That is very slow to adapt, in my opinion. So as you can see, it is just not going to be scalable or sustainable with this sort of operations, and we need to really solve automated continual learning directly on the autonomous car. The key limitation of the current AI systems is that they only compute with what they have been programmed or trained for in advance. But there is just no way we can create a training set for all possible situations that one encounters in the field. Unfortunately, the current AI still follows the 1936 Turing model, wherein the mainframe loads a program, and then it processes the inputs exactly as instructed by the program, just like how our car is programmed to be in the lane and not to do other things, like responding to a human worker in a work zone. Not just the rule-based programs, but also the machine learning programs, they still follow this paradigm because once they are trained, they're frozen, they are fixed. From the theoretical work of Dr. Hava Siegelman, who is our program manager, we know that we need to do better. We need to go to a higher model. In fact, there is a continuum of computational models ranging from fixed program-based Turing machines to modifiable program-based super-Turing machines, allowing for exponentially more input-output functions. So if we really are serious about making AI truly intelligent, then we need to go beyond the Turing paradigm. And that is the reason DARPA created Lifelong Learning Machines program. So let's look at the plot at the bottom. Just to summarize, current AI learns from billions of training examples and exhibits a high performance during fielded operation until there is a surprise. And then excuse me. On the other hand, what we're trying to do in this program is to build a machine that follows the green curve, which learns from new experiences, adapts to change, and continues to improve. So in the remaining part of my talk, I would like to share some of our recent successes. We just finished about a year on the program. The first capability relates to dealing with unexpected changes, like sensor failure. Columbia University recently developed a method for a robot to auto-generate its own self-model. So essentially, they used a sequence-to-sequence model, which is like a deep network, to learn a self-model which is basically modeling the entire forward kinematics without any assumptions about the physics, geometry, or motor dynamics. You can learn the self-model from random trajectories of the robotic arm. So here you can see the self-model superimposed on the real robot. Initially, the self-model is very inaccurate, but after a day of training, it becomes consistent with the physical robot to about within 4 centimeters. So the self-model is good enough for the robot to use a simple internal planner to do to pick and place a task with 100% accuracy. The same self-model can be used without any additional training for new tasks. And then it can also be used to detect changes to its own morphology. And once the self-model is reimagined, then it can adapt and get back to the task without any further degradation in performance. The second capability relates to learning from massive amounts of unlabeled data, which is the case for autonomous cars as they're driving around on the roads. This notion is called self-play or self-supervised learning. A number of teams are working on this. Just to give you an example, Toyota TIC has shown that it is possible to extract relative depths of objects in a scene from a monocular camera without any supervision, using the principle that nearer objects tend to move much more compared to the farther objects as the agent navigates through a scene. UMass Amherst is using such self-learned associations to perform fast searches of relevant objects in scenes. Just as an application, just imagine a car that is driving up to an intersection with lights. Based on prior experiences with similar other intersections, without any supervision on the spatial relationships of the task-relevant features, the car can direct its attention to the locations of the lights, pedestrians, and other cars. So there is a lot we can do without label data. At HRL, we are working on a novel machine learning paradigm, which is end-to-end, which is very applicable to autonomous cars. We call our architecture SUPER-TURING, Evolving Lifelong Learning Architecture. So we actually work on a range of aspects from perception, memory, planning, and the controller. Just to drive home the motivating example, please imagine your daily commute to your work. On my daily commute, if I encounter a surprise, I adapt almost immediately without any delay. But on the other hand, my autonomous car may take up to 50 days to deal with that surprise. One solution is to leverage the fleet of autonomous vehicles. If enough of them are driving my particular commuter route, then perhaps my autonomous car can deal with that surprise a bit faster, maybe in 5 days, which is still, I would say, slow. But just imagine a future where every car that we see on the road is going to be autonomous, every single car. And that is, each car is then just going to generate massive amounts of data and to the cloud, trillions of miles. So we will be very soon in a future where it is just not going to be possible to store every mile of data from every car and then retrain with all of the data whenever a single car in the fleet encounters a surprise. So we just need to solve this problem once for all. Deep neural networks suffer from what we call as catastrophic forgetting. So essentially, you have a deep network, you train it on one task, and then you bring in a new task, then the parameters are overwritten. So it becomes optimized for the new data, but then because the parameters are overwritten, it forgets the old task. So this is known as catastrophic forgetting. And the reason it happens is because a neural network, however deep it is globally changing whenever there is a new experience. And that is the reason it is forgetting. So one strategy to deal with this problem is to automatically allocate different parts of the network to different tasks. So say our autonomous car has been trained to recognize a stop sign, and we want to preserve that capability as it explores new experiences and learns in the field. One way we can deal with that is to use the phenomenon of attention. If I asked you to pay attention to my hand right now while ignoring everything else, then you can so easily do it, right? So similarly, we can tell the network to pay attention to the connections that are most critical for this task and not for anything else. So those are the green neurons in the network. And once we determine those important neurons for a task as the learning is happening, then we can define the connections between those important neurons to be critical for the task. And then we gradually reduce the learning rate on them so that we can preserve the knowledge that is embedded in those connections to be able to recognize the stop sign. As a proof of concept, we trained a deep network to perform digit recognition. So here, the network has to recognize digits from 0 to 9, but then it is first trained on 0 and 8. So the first task is to distinguish 0 from 8. Once that is done, so during deployment, say it is challenged to distinguish 7 and 3, then 6 and 2, 1 and 5, and 9 and 4, in that sequence. This is how neural networks operate. So this is the phenomenon of forgetting. So the different colors represent the performance of the network on these 5 tasks. So as you can see, so these are the sequential training. So as you can see, the performance is higher, but then with the introduction of each new task, the performance on the original task keeps dropping. And we can avoid that with our method of top-down attention to figure out which connections are important and then preserving the knowledge accordingly. I want to give you another nugget that we use. It is inspired by a phenomenon that happens every single night when we sleep. You may have heard it. It's called replays. They happen during stage 3 and 4 of non-REM sleep. So essentially, as you may know, our brain has two memory systems, the hippocampus and the cortex. The hippocampus learns rapidly, but also forgets rapidly. On the other hand, the cortex learns very slowly, but it holds all of our remote memories. Both the hippocampus and the cortex are trained to model the world dynamics. So that is to predict the next frame in the experience. So here again, you don't need any labels because the input is the current frame and the output is the next frame. And you get that information directly from the world if you just wait one time step. So during sleep, if the cortex, which is the slow learning memory, if it can create necessary prior experiences, and then if the hippocampus can replay recent experiences and we interleave them, then we will be able to solve the problem of catastrophic forgetting, even when we don't have any access whatsoever to the original training data, which could be trillions of miles in the autonomous car case. So as a proof of concept, we exposed our memory network to 6 Atari games in sequence. So for each game, the task is to predict the next frame in the game. And then we are looking at the accuracy of the predictions of the game. So this is the baseline. So here, we are trying to reconstruct the experience from the Atari game called River Raid, which is task 0. So as you can see with the exposure of more Atari games, the predictions become very erroneous. So there is more than 100% increase in the error for the predictions. But if we can incorporate replays, then there is no loss in the prediction. So here, lower is better. So here we can reconstruct the original game almost perfectly, despite being exposed to other games in sequence. So, so I just want to conclude with some thoughts. So I talked about a lot of things, but essentially we want the autonomous cars to be able to rapidly adapt to and learn from novel, surprising situations without forgetting. It's very easy to adapt, but then if you want to adapt without forgetting, that's the key challenge that we are trying to solve. So I think the car has to be very attentive when driving so that it can consolidate the old knowledge, and then it has to dream when it is parked so that it can overcome the problem. And so if we are very serious about achieving level 5 autonomy in cars, then we really need to solve lifelong learning first. Okay? So on Wednesday, we are going to have a workshop on the program. There will be other speakers. We'll go into a lot more detail. There will be more applications of this technology. And then we are actually going to have a panel on hardware for L2M. With that, thank you.